Okay, so again, working through some examples of logarithmic and exponential applications. So we've looked at exponential growth, exponential decay. We've talked about logistic. Got to spell it right first. Logistic growth. So this was the case where you had exponential growth initially, but then you had limited resources. And we said that the function for the quantity was usually some number, we'll call it the carrying capacity, divided by 1 plus b times e to the minus kt. And what you end up with is this function looks something like this. It starts with some initial amount and it grows exponentially, but then you have competition for resources, and then it ultimately reaches the carrying capacity. So this would be, the initial amount, p0, t equals 0. As t goes to infinity, then the value approaches the carrying capacity. You can see what would happen is as t goes to infinity, you go e to the minus infinity, and e to the minus infinity is 0, so this whole thing goes to 0, and you just end up with L over 1, which is L. So in this case, you have to be given three things, because you have three constants, L, B, and K. So the things that you're usually given are the carrying capacity, which is L. You're also given the initial quantity, so that's P of 0, and you're also given the quantity at some time t, so P of t equals something. And from those three things you can calculate each one of these constants. So let's say the carrying capacity, and this is going to be, I'm going to say it's wolves in some ecosystem. So let's say the carrying capacity is 3,000 wolves. And the initial quantity, so P of t equals 0, P of 0 equals, say, 250. So you have this ecosystem, you introduce 250 wolves, and what you see is the number of wolves at t equals 10 years. So P of 10 is, well, it's going to be more than 250 and less than 3,000. So I'm going to say 780. So the first thing you do is calculate, well, really don't have to calculate because it's given. So you'd say, P of t is going to be equal to 3,000 L divided by 1 plus b e to the minus kt. So that takes into account that. The second thing you do is use P of 0, which is going to be 250, is going to be equal to 3,000 divided by 1 plus b e to the minus k times 0. So what this does is it allows you to calculate b, because this whole thing equals 1. So you get 250 is equal to 3,000 divided by 1 plus b, and you just have to solve for b. So what I usually do is I take this number and switch it with that number, because you've really got two ratios. 250 over 1 is equal to 3,000 over 1 plus b. So I can say 1 plus b is equal to 3,000 divided by 250. So let's go ahead and calculate what 3,000 divided by 250 is. 12. Then you subtract 1 from both sides to solve for b. B equals 11. So now at this point we know 2 out of the 3. So it's 1 plus 11 e to the minus kt. And you can see when t equals 0, this goes to 1, so you have 1 plus 11, which is 12. 3,000 divided by 12 should be 250. 3,000 divided by 12 equals 250, so that's true. Now you do p of, use the value here, p of 10 equals 780. Is that right? 780. Yep. And we're going to solve for k now. So you have 3,000 over 1 plus 11 e to the minus k times 10. So we can do the same thing. You can switch. You can do these two ratios. So you get 1 plus 11 e to the minus k times 10 equals 3,000 divided by 780, and 3,000 divided by 780 is 3.846. Let's make this minus 10k here instead of minus k10. So it's going to be minus 10k. Subtract 1 from both sides. Get 2.486 divided by 11. So let's go ahead and do that. So you get 0.25874, and then you take the natural log of both sides to get the exponent down out of the, get the unvariable out of the exponent. So the natural log of e to the minus 10k is minus 10 times k. The natural log of .25874 is negative 1.3519. Divide both sides by negative 10. That solves for k. And you get 0.13519. So the final answer for the equation of the population in this case is going to be equal to the carrying capacity, which we said was 3,000, divided by 1 plus 11e to the minus 0.13519 times t. So that's the equation. And then if you wanted to figure out what the, well, let's actually ask the question, how long does it take to have 1,500 wolves? So that's half the carrying capacity. What is the time? So we have to solve for t again. Well, in this case we don't. We just have, in the last case we solved for k, but it's it's basically the same series of steps, except we're solving for t in this case instead of for k. So you get 1 plus 11e to the minus 0.13519. T is equal to 3000 divided by 1500, which is 2. Subtract 1 from both sides. 2 minus 1 is 1. 1 minus 1 is 0. Divide by 11. So you get 1/11th, which is 0.0909090, is it? Okay. Dun, dun, dun. Okay, then you take the natural log of both sides. So the left-hand side just becomes negative 0.13519 t, and the right-hand side is the natural log of that quantity, which is negative 2.3979, and then divide both sides by negative 0.13519. And remember, let's see, it took 10 years, is that right? 10 years to get to 780, so it should be more than 7 years. And it turns out to be 17.7 years. So that makes sense. Okay, so those are logistic growth problems. So again, what we do is you typically given carrying capacity, an initial amount, and the data at one time. From the carrying capacity, that's easy. That's just the numerator. From the initial quantity, you can calculate B. From the quantity at a particular time, you can calculate K. Once you do that, you get the equation. And then you can evaluate, it at a particular time, or you can ask what time, how long it takes to get to a particular quantity. So those are the main three kinds of exponential problems: exponential growth, exponential decay, and logistic growth. You'll see those again in calculus. So when you see this, you'll be able to ace. You'll be able to do well on those particular problems. The last example is I'm going to talk about sound. And this is a case where you have logarithmic functions. And so what we say is that the sound level in decibels is equal to the 20, I think it's 20, maybe it's 10, it's probably 10. Times the log to the base 10 of the intensity of the sound divided by this reference intensity. So I0 is just a constant, which is 1.0 times 10 to the minus 12th, and it has units of watts per meter squared. So this is energy, watts per unit area, meter squared. So that's I0. And so we might have the sound level in decibels and then have to calculate what the actual sound level intensity is. Now, if you're given the sound level here, I, it's just a matter of evaluating this logarithmic expression. Okay, so that is correct. So basically the question would be is what is I when the sound is 75 decibels. So what you end up with is 75 is equal to 10 log base 10 of I over 1 times 10 to the minus 12th. And this is watts per meter squared. Now decibel is unitless. Just like with E, the units for log are unitless and 10 is unitless. So for one thing, I has to have the same units as this, which is true, watts per meter squared. So to solve for I, what we do is we take both sides and divide by 10. And then to solve for I, we take, you might think, oh, we take e to the 7.5, but you have to use the same base as the logarithm that's used here, so it would be 10, the base, to the 7.5 power is equal to 10 to the log base 10 of I, what we're trying to solve for, 1 times 10 to the minus 12 watts per meter squared. So 10 to the log base 10, again, because these are inverse properties, the exponential function 10 to the x is inverse of the log base 10 of x. So what you end up with is I divided by 1 times 10 to the minus 12 watts per meter squared is equal to 10 to the 7.5, which is not equal to, well, yeah, so what is that? 10 to the 7.5 power. It's not 7.5, 10 to the 10, it's, let's see, 10 to the 7.5 power is equal to 3.16 times 10 to the, let's see, 1, 2, 3, 4, 5, 6, 7, 10 to the 7th. So I just stuck that in my calculator. So, 10 to the 7th is the same as 1 times 10 to the 7th. And 10 to the 8th is 1 times 10 to the 8th, obviously. But 10 to the 7.5 is somewhere between these two, which this is. Okay, so now I is just going to be equal to 3.16 times 10 to the 7th times 1 times 10 to the minus 12th watts per meter squared. So the final units are watts per meter squared. So you'll get 3.16 times 10 to the minus 5 watts per meter squared. Okay, how did I do that? Well, 1 times 3.16 is 3.16, and 10 to the 7th times 10 to the minus 12th, because these have the same base, you add the exponents together, and you get that value. Okay, so that's all we're going to do with some examples.